Curves and Surfaces, a third-year project by Lois de Cordova and Ray and Lois.
What are curves and surfaces? A curve is similar to a line, but is not necessarily straight. It has defining features, such as curvature, which is our main theme for this video.
A surface has length and breadth, but no thickness. If you look at the donut, which is mathematically called a torus, you might think that it has thickness. However, it's actually hollow, and if you were to unfold it, it would be a flat surface.
Let's go back to 1684, where the story of curves and surfaces began. Newton and Leibniz tried to deal with the curvature of plane curves with Leibniz's first attempt of a definition.
In 1736, Euler initiated intrinsic geometry and introduced the notion of arc length and curvature radius. Euler did eventually start working on the theory of surfaces in 1748 and introduced the first notion of curvature in 1767.
The study of space curves started in 1771 with the work of Monge, but Cauchy introduced the modern way of defining notions such as curvature and torsion, and later Darboux gave the first modern description in terms of moving frames.
Gauss's work in 1828 systematically studied surfaces and introduced the curvature nowadays known as Gaussian curvature. From the diagram, we can see that if a triangle were placed on the object, if its total angles were less than 180 degrees, then it would have negative curvature. Equal to 180, zero curvature, and if it's greater than 180, positive curvature.
Let's take a more detailed look into those plane curves, space curves and surfaces that we mentioned earlier.
This is a plane curve. It's called a plane curve as it only exists in the 2D xy plane. The first component is x and the second is y. We want to find the curvature of this curve, i.e. the rate of change of the tangent. Let's take a look at our original curve. This is our curve differentiated, i.e. the tangent. You can see the tangent moving along our curve in the animation.
We can find curvature using this formula. So, by plugging in gamma prime and gamma double prime, we find the curvature of the curve to be this. It doesn't look very nice, but we've done our job. This is a space curve. It's called a space curve because it exists in 3 dimensions. The first component is x, the second is y, and the last z. Have a look at our plane curve. Now take a look at our space curve. It looks remarkably similar to our plane curve, just slanted.
Let's take a look at our original space curve. This is our space curve differentiated, i.e. the tangent. We want to find the curvature and torsion of this space curve. Torsion is the extent of which a curve departs from being planar and is often referred to as a second curvature.
Also from the animation, you can see how the Frenet frame dictates the movement of the curve by using the tangent, binormal and normal vectors. The binormal vector is orthogonal to the tangent and normal vector.
We can calculate the curvature of the space curve by using this formula. Now to find the torsion of the space curve, we can use this formula. We find the value of the torsion to be 0. Here we have a surface XUV, which is a 2D object in a 3-dimensional space. The first component is x, the second y, and the last is z. It has been parametrized by 2 variables u and v.
In the animation we can see our space curve on our surface. Note how our plane curve, space curve and surface all interact in some way. Like with our plane and space curves, we want to find the curvature of the surface. However, a surface has 2 different types of curvature, Gaussian curvature and mean curvature. We find these by computing the first and second fundamental forms.
To find the coefficients of the first fundamental form, we use the following equations. So we must partially differentiate our surface with respect to u and v. In the animation, we can see the partial derivatives xu, which is orange, and xv, which is blue. Plugging these values into the formulas, we obtain e, f, and g. Note that the coefficients e and g are the same.
In order to calculate the coefficients of the second fundamental form, we need the unit normal vector n composed with x, which you get from this formula. We also need to compute the second order partial derivatives of the surface, and then plug them, along with nx, into these formulas to obtain our coefficients.
Now, if we simply plug the values into the formulas we saw earlier, we obtain the Gaussian curvature and mean curvature. We can see that the mean curvature is 0, which means that the surface xuv is a minimal surface. A very famous result of Gauss's explains why every map from the Earth's surface has to distort distances, and why the Earth and a plane have different Gaussian curvature. The basic problem of mapping the globe is how to transfer the curved surface of the Earth, an oblate spheroid, onto a flat surface.
In map projections, there are a variety of things that you want to preserve, such as area, distances, angles in triangles, and so on, but the trouble is you can't preserve them all.
Famous projections include the Mercator's projection in 1569, as shown. Here we can see that Greenland looks the same size as Africa, when in reality you could fit several Greenlands into the whole of Africa.
On the other hand, the Peters projection map is a version of the world map in which areas of landmass are shown proportionately.
There are many other applications of curves and surfaces used in a variety of different fields, from physics to economics and engineering to geometric modelling in computer systems.
However, unfortunately, we can't mention them all in this video. We hope this video has been informative and you have enjoyed watching it.